Welcome to this lecture series in complex numbers. In this lecture, we'll be doing a general discussion about polynomials and roots. So let's get started. We saw the notion of nth roots of a complex number. So fix a complex number z0 and a positive integer n. Then an nth root of z0 is a complex number z, which satisfies this equation, meaning if you raise it to the nth power, you get z0. We saw that if z0 is a non-zero complex number, then there are exactly n distinct nth roots of z0. All right. So we need the notion of a polynomial. Fix a non-negative integer. A polynomial of degree n over the field of complex numbers is a function from C to C. So this notation just means that it is a function which consumes a complex number and produces a complex number. Not to say that it produces all complex numbers as its output. That is not what is being said here. It's just that it takes any complex number as an input and produces a complex number as an output. So a polynomial of degree n is a function such that there exist complex numbers a0 up to an, with an being non-zero, such that fz is this expression, right? So basically it's sums of scales of powers of z, and the highest power that you see is the nth power because an is non-zero. So I'm sure you were familiar with this definition, but anyway, so let's look at some examples. So if I define fz as 2z square plus 5z plus 9, that's a polynomial. Or one can even define fz as some constant, let's say 4 for all z. This is also for all z. This notation means for all. So such things are also polynomials, and it is a polynomial of degree 0, as you can check. And they are also called constant polynomials because they take only one value. They are constants. All right, so very simple concept. We need the notion of a root. So fix a polynomial. We say that a complex number z0 is a root of f, the polynomial f, if this happens. F vanishes at z0. All right, so that's the definition, and here is a very nice theorem about roots. So f is some polynomial, and z0 is a root, and the theorem says that z0 is a root of f if and only if there is some polynomial g such that fz is equal to z minus z0 times gz for all z. So you can write fz as the product of these two polynomials. Basically, this is the polynomial coming from z0, and this is some polynomial. And clearly, if fz is equal to that for all z, then it is clear that z0 is a root of f, because f of z0 is what? F of z0 would then be z0 minus z0 times some number, which is 0. So if this is the case, then clearly z0 is a root of f. For the converse direction, we will do something better than, we have a more general statement that we will look at. The converse direction is that if z0 is a root of f, then you can find a polynomial g such that this happens. So we have a more general statement, and that statement is this. Suppose we have some polynomial and some complex number z0. Then there exists some polynomial g such that f of z is this expression that we saw earlier plus f of z0. So once we are given that z0 is a root of f, this part just goes away and we get this. So let's just prove that, and let me prove it by means of an example rather than doing the full details. It is better to look at just one example. So say f is this polynomial 2z square plus 5z plus 9, and we want to find a polynomial g such that this happens. And let's say z0 is, let's say 7. Okay, so the idea is this. We will write f of z as twice of z minus 7 plus 7 square plus 5z minus 7 plus 7 plus 9. So note that this is just z and that is also z. So clearly f of z is equal to that. And now we just expand the brackets. So this is z minus 7 whole square plus 14 z minus 7 plus 49 plus 5 z minus 7 plus 35 plus 9. Just expanding the brackets, so this is equal to twice of z minus 7 whole square plus 28 times z minus 7 plus 98 plus 5z minus 7 plus 44. And we can add these two things, so we get twice of z minus 7 whole square plus 28 plus 5 is 33 z minus 7 plus 98 plus 44. 98 plus 44 is what? It's 142. Right, and here we can take z minus 7 as common, and in the bracket we get something. (142), and this is g of z. 7, remember, was z naught, and 142 one can check is nothing but f of 7, because what is f of 7? F of 7 is twice into 49 plus 35 plus 9, which is 142. So this is the idea basically. If you follow this idea for any polynomial, then we get that. All right, this is called the remainder theorem or something. It has a name. Okay. So now we come to a very fundamental theorem in mathematics. It's called the fundamental theorem of algebra. It says that if we have a positive integer and a and a polynomial of that degree, so we have a positive degree polynomial, then we claim that it has a root. It has there is some complex number at which it vanishes. Of course, you need this condition of positive degree, because if you have a constant polynomial, then clearly it may not vanish at all. So this is called the fundamental theorem of algebra, and it's not easy to prove. We will take this for granted. This is beyond the scope of high school mathematics, the proof of it. All right. So a consequence of this and the previous theorem is the following. Fix some positive integer and f be a polynomial of that degree, so a positive degree polynomial. Then we can find, so whatever is this n, we can find n complex numbers, not necessarily distinct. There may be repetition here, and some non-zero complex number a, such that f of z can be written in this fashion. Right? It's looks like a particularly simple thing. And these z1 up to zn are precisely the roots of f. So how do we see this? Basically, start with a polynomial. It has some root, as we know from the fundamental theorem of algebra. So whatever be the root, call it z1. And then you can write it in this fashion by the theorem that we saw earlier, this theorem. Because of this theorem, we can find another polynomial such that fz is equal to this. And then play the same game for g. So this will become z minus z1 into z minus z2 times some other polynomial hz, and this will go on unless the degree of this guy becomes 0, in which case this is a constant, and that constant is what is appearing here. So it's a immediate consequence of the fundamental theorem of algebra and the theorem that we saw earlier. Okay. Now we come to a very important theorem called Viete's theorem, and before I state it in full generality, let us look at a special case, and then we will state the general theorem. So suppose we have a degree 3 polynomial. Fz is this form, and of course it will have 3 roots. Again, there may be repetition here. So z1, z2, z3 be 3 roots of it. Then one can see that fz is of this form by the previous statement, this one. So this constant must be a3. One can verify that. So fz is of this form, and if we expand this, mindlessly, then we get this is equal to a3z cube a3z cube minus a3z1 plus z2 plus z3 z square plus a3 z1 z2 plus z2 z3 plus z1 z3 z minus a3 z1 z2 z3. So this is just a matter of expanding the brackets. And now we have two different ways of expressing f. So one expression is this, and the other expression is this yellow one. And it so happens that if you have two different expressions of the same polynomial, then the coefficients must agree. So what are the coefficients? These numbers are coefficients. Here, these are the coefficients. These things. So, sorry, this entire thing is a coefficient. So the coefficients must match. And how do we see that? Basically, if we evaluate f at 0, then this part goes away. So f of 0 has two expressions. F of 0 is a0 by the first one, and f of 0 is also equal to that. So we see that this coefficient must match with that coefficient, and you can slowly work your way up to other coefficients by this kind of trick. There are other ways to show that the coefficients must match. You can also differentiate, although it's a complex valued thing, so perhaps you're not familiar with complex differentiation, but you can just say that, okay, just feed real values in it, and you can do the real and imaginary part business also, and then differentiate. Anyway, you can figure out why the coefficients must match. So if we match the coefficients, what we get is we get that z1 plus z2 plus z3 is minus a2 upon a3. z1 z2 plus z2 z3 plus z1 z3 is plus, so it's just a1 upon a3, and z1 z2 z3 is minus a0 upon a3. So that's immediate from matching the coefficients. So what is happening is the sum of roots is given by that. Denominator is a3. The sum of product of roots taken two at a time. So you pick two roots, product them, and then sum all the products. So if we pick these two roots, the product is z1 z2. If we pick these two roots, the product is z2 z3. And if we pick these two roots, the product is z1 z3, and we add all of them. So that sum is given by this. And similarly, if you pick all the three roots and product them, then the result is this. So it comes alternately with minus, plus, minus signs, and the coefficients for the sum of roots, you get the coefficient of the penultimate power of z. So this is the ultimate power of z, the highest power. Here you have the penultimate power, and then the coefficient of the ultimate power. Here you have the coefficient of z to the power 1, and then the ultimate power, and so on. So this is an instance of Viete's theorem. The general theorem is the following. Fix some positive integer n and fix a polynomial of degree n. Say f of z is of this form, and these be all the roots. Then the sum of roots, taken one at a time, is minus an minus 1 divided by an. The sum of product of roots taken two at a time. So pick two roots, product them, and then add all the products. So that can be written succinctly in this fashion. That is an minus 2 divided by an. The sum of roots produced three at a time is minus an minus 3 divided by an, and this goes on. Ultimately, we have the product of all the roots, that is minus 1 to the n, a0 divided by an. So this goes alternately as alternately as minus, plus, minus, plus, and so on. And this is the way you can express all of these things. So that is Viete's theorem. And yeah, let's move on. Lastly, we can revisit the notion of nth roots in this new language. So fix a complex number z0 and some positive integer n. Define this polynomial by this formula, fz equals z to the n minus z0. Then just note that the nth roots of z0 are precisely the roots of the polynomial f. And there's nothing to say about it. It's just immediate from the definitions. So basically, we have a more general notion of roots rather than just nth roots. You can talk about roots of polynomials, and nth roots are special instances of that notion. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.